Hello, everybody. So what we're going to be looking at today is just sample problems, really. So we're just going to look at some sample problems from sections 1.5, 1.6, and 1.7. So some proofs, some arguments, and I don't know what else. So let's go ahead and get started and see where we end up. So the first thing I want to do is I guess this is one of your homework problems, but I'll go ahead and do it anyway. So somebody sent me an email and asked me to do problem 1.5.43. So we will start there. So what 1.5.43 says is it says we need to express, they say using logic, blah, blah, blahs, but express the fact that linear polynomial, every linear polynomial with degree 1 with real coefficients and where the coefficient of x is non-zero. So I'll just say with non-zero coefficient on x. Has exactly one real root. All right. So that's how it's worded. Well, no, it's not actually how it's worded in the book. I kind of rephrased it a little bit. Um, Now, something I want to mention is I did actually look and I found like the solution. I saw this in the solutions manual and I didn't like the way they did it. So we have these symbols. So we have this symbol, right, for all x. We have this symbol, right? This is for all x. This is there is at least one x. And then we had there exists a unique x, right? And so I think that's what we had. And I'm actually slightly worried that, well, not worried, but they might not actually use that uniqueness symbol in this section. I'm sure they use it in the book, but I think they might like wait and give it to you in a different section. But if you have this uniqueness symbol, it really makes this problem a lot easier because when they say exactly one, then that's what they mean, a unique real root. So this is there is exactly one x. Okay. And so if you know that, then this is really a lot easier than the way the book would try to make it. So what I want to do is I want to actually rephrase this a little bit. So when they're talking about every linear polynomial, what is a linear polynomial, right? That kind of stuff. So let me rephrase it and be a little more exact or precise in my um, words here. So here's another way to say it. For all m and b. Now, why am I saying m and b? Because we're going to be talking about mx plus b, right? So mx plus b is a linear polynomial. So for all mx plus b, or maybe even for all real numbers, that's probably how I should say it. Put that over there for all real numbers, m and b, if m is not 0. Now I want to say m is not 0 because m is the coefficient on x, and what we say up here is it says non-zero coefficient for x. So if m is not 0, then what? Then there's supposed to be exactly one root. Then there is exactly one x with what property? Well, the property is that the x needs to be a root of the polynomial. So exactly one x with property mx plus b equals 0. So there's only one x that satisfies that, and then that would be the root. Okay, so that's just hopefully rephrasing the original thing there. So once we rephrase it though, the way I worded it here is much closer to the way you have to write it if you're going to write logic symbols. Okay, so let's try to do this now. So let's start at the top here. For all real numbers m and b. So you just say, like, for all, we're just going to say m and b, and afterward I can say, where m and b are chosen from real numbers. But for now, let's just say for all m and for all b. Okay, so we have that. And after we have that, then there's an if-then statement, right? We have if this, and then you have then this. So that's an if-then. So that's a conditional statement. So the first part of the conditional statement is if m is not equal to 0. So m not equal to 0. If that, then the other statement, the one in yellow, there is exactly one x with mx plus b equals 0. How do we say that? Well, to say there's exactly one x, you say there exists a unique x. And then what property does that x have? Well, it's that mx plus b equals 0. And that's it. So that's how I would write this. Okay. So we have for all m, for all b, if m is not equal to 0, then there is a unique x such that mx plus b equals 0. Okay. Yeah, I mean, so that's how I would do it. And the alternative way is similar to this, but it's kind of a pain. So if you don't have the uniqueness symbol there, the exclamation part that we're using for that. So without unique, what you would have to do is slightly different. You would have to say for all m, for all b, so that's the same. If m is not equal to 0, then there exists an x such that mx plus b equals 0. Now, that looks the same, right? But the problem with what we did here is what I just wrote says that if m is not 0, then there is an x to satisfy that equation. So there is a real root. Well, I didn't say real, but there is a root. Now, how do you say there's only one root? And the way you have to say that in mathematical symbols is a little bit awkward. So the way you have to say, like the way that you say things are unique is by saying if there's two of them, they're equal, right? So this idea, sorry, like blowing a piece of dust off my iPad here. Okay, so what are we doing? So the idea behind uniqueness is this. So the way, like, if you needed there to only be one thing, you say something like this. If, X satisfies some property and Y also satisfies the property, then X has to equal Y, right? If you say that, then you'd be saying, like, okay, assume we have two different things that satisfy a property, X and Y. Well, if we have two things that satisfy the property, actually they're the same thing. Well, if that's the case, then that's how you would be saying that there's only one of them, right? Because we're saying if you have two of them, they're actually the same thing. So then there's not really two of them, are there? Does that make sense? So that's what you have to do um, to write uniqueness without uniqueness. So what we've got up here so far is this is there is a root to the equation, or yeah, to the polynomial has a root. But to say that there's a unique root, you would have to add that extra bit. So you basically need to write this in symbols. So you'd have to say, and if you had two different roots, right? So if this was satisfied by two different numbers, so like if mx plus b equals 0 and my plus b equals 0, right? So there's two roots. Y and x are both roots. That would imply that x equals y. And then that's how you would do your uniqueness. So we've got x is a root as an x, y is a root, and together those actually imply that x is actually y. And that's how you say that there's only one thing. Because if there were two of them, they actually must be the same thing. If there's an x and a y, actually x equals y. So there's not, x and y are not separate. Okay, so that's how you have to do it. So without uniqueness, you have to tack on this kind of thing onto the end, and it's a pain. And so that's why it's good to have, obviously, this symbol here, so you can say there exists a unique x without having to explain what unique means, which this is what unique means. If there's two things, they must be equal. So really, there's only one. Okay. So again, I would definitely recommend you do it the way that I did it in the box, even if that does not match the answer in the book. Go ahead and use the uniqueness symbol. Save yourself some time and effort. Okay, so that's it for that one problem. What do I want to do next here? I think I want to move on and go to section 1.6, I think it is. Let me see. Maybe I'm wrong. No, I'm not wrong. That's what I want. So section 1.6 is on rules of inference and logic and, valid argument. So I want to do 1.6.15D. I think D is not assigned, right? Isn't this assignment do parts A, C, E? So I guess I could do B, but I didn't look at B, so I'm going to do D. All right, 1.6. That's a highlighter still. 1.6.15D. All right, so what are we doing in this section? So what we're doing is we are determine if the argument is valid. Okay, so what's the argument in 15D? So the argument is everyone that eats granola every day is healthy. Also, they are crazy. What's next? Linda is not healthy. We have that in common, she and I. I didn't eat granola today, but I did eat some Hostess Ho-Hos. Think they're just as good for you. Therefore, Linda does not eat granola every day. All right, so that's the argument, okay? And we need to determine if it's valid, all right? Now, typically the way these work is you just translate them to symbols and then you write them down. And usually there's just like one or like there's like one line missing or something like that. Sometimes there's not even a line missing, but that's the basic idea. So like, how would you do this? Well, the way you would do this is first of all, define your predicates. So let's say like g of x be x eats granola every day, right? So g of x for g for granola, and then let h of x be x is healthy. All right. So the argument as they have it is this. So their argument is this. Their argument is then uh, everyone that eats granola every day is healthy. The way you would write that is you would say everyone, that would be all x. X are people here, right? I didn't say that, but it's clear from the way I used it in the previous two lines that x is a person. So for all x, uh, it says everyone that eats granola every day is healthy. That means for everybody, if you eat granola, if X eats granola, then X is healthy. So that's how you would write that top line. The next line is Linda is not healthy. So that would be healthy is H. So not healthy would be not H. And then the specific person we're talking about is Linda. So Linda is not healthy is like that. And then therefore, so we're at the conclusion. Therefore, Linda does not eat granola every day. So G is X eats granola every day. So if Linda does not eat granola every day, then that's not G. So not eating granola. Who does not eat granola? Linda. Okay. So this is the argument. So this is their argument, and we have to decide if it's valid. We haven't even done that, right? All we did was we wrote their argument down. And so there's no real shortcuts to this. Basically, what you do is you start with their uh, premises. So you start with this and you see if you can get to this. Okay. And you just try to apply valid logic. So start with the premises and see if you can get to the conclusion. And there's not really another way, because they're telling you what the conclusion is or is supposed to be, but they don't tell you what logical steps you're supposed to apply. So you don't know how many steps there are or anything like that. They didn't say. So it's not just a simple matter of, oh, is the third line come directly from the previous two? No, you've got to actually do more work than that. So you start with the premises and see if you can get the conclusion. Okay. No shortcuts. So the way I'll start it is I'll say, okay, well, let's write what they have. So I'm just basically recopying what they have. So, and then I number the lines so I can refer to them. All right. So the first one is there. The second one is not H of Linda. Okay. So now what we do, so this is my argument. What I'm going to do is I'm going to try to come up with new lines of work that come from these old lines of work. Okay. So how do we do that? So what you do is something like this. So this first line says, for all x, g of x implies h of x. And we know that we have universal, what do they call it? They call it universal instantiation, right? That's where you go like this. Like if all x, p of x, if you're able to conclude p of, a specific example, like any, they just write p of c, but like p of any example. right? Because if P is true for all X, then no matter what you put in P, it must also be true. So if we're talking about Linda here, basically what I want to say is take a look at that top line. That top line is true for all X. So the top line must also be true for Linda, right? Linda's a person, and this is for all people X. So if you rewrite the top line with Linda, you would get G of Linda implies H of Linda. Okay, so this is line 3. Maybe actually I want to maybe write these on the other side here. 1, 2, 3. And then write the justification here. So what did we do? We used universal instantiation. Instantiation means we put an example in. Generalization means we went from the example back to the for all. So universal instantiation. Okay, and that's from 1. Okay, so you see how this third line did not appear in the original argument, but I'm writing it because I think it'll help me reach the conclusion. Okay, now I'm looking at this right here, and actually I see something. What I see is a structure here that I've seen before. And I've seen that before in what they call like Modus Tollens, I think, right? So Modus Tollens says this: if you have P implies Q and you have not Q, then the conclusion is not P, right? So you have to look in the book to see if that's true, but I think that is Modus Tollens, right? Um, so, um, right, like what we got is like this is your, let me pick a color here. Like this is your P implies Q right here. And then this line above it is your not Q, right? Because it's not H of Linda. So the conclusion would be not P, wouldn't it? It would, right? Not P. So not P would be not G of Linda. So if you apply Modus Tollens to these two lines, you would get line, what I'm going to call line 4. The conclusion would be not G of Linda. And that is Modus Tollens from the previous two lines, 2 and 3. And actually that says G, remember G is eats granola every day. So not G means Linda does not eat granola every day, which is actually, right? What's it say here? Linda does not eat granola every day. That's actually the conclusion that you were supposed to reach. So this is actually, I don't even need to number it then. I can just, therefore, right? So that's it. I did it. I proved I actually was able to reach their conclusion. So since I was able to reach the conclusion, which is Linda does not eat granola every day, then that is a valid argument, right? The argument was valid. But there was no way to know other than to actually do all this work that I just did, right? You had to just try to prove it. And since I was able to actually work out this argument here, yeah, it's valid. Okay. And so that's what you're expected to do. Now, the problem with doing it this way is if you don't get to the answer, right, that could mean that the argument was not valid, but it could also mean that you just, it's valid, but you weren't able to do it, right? And that's really the same kind of problem you have in the next section where you're doing proofs, right? If you're supposed to prove a theorem and you can't, well, does that mean that nobody can prove it? Or does that just mean that, you didn't do a good job proving it? So it it's kind of tricky to do these. You're just trying to get to the answer. If you do, it's valid. If you don't, probably invalid, but maybe you just suck. I mean, they're hard. Some of them are hard, right? So, like, I shouldn't say like maybe you suck, right? Like, probably I suck. If you ask me to do the problem, then I will fail, and then I suck. All right. Okay, let's do a different problem. I feel like this problem reminded me of grape nut cereal, which is like the worst cereal I've ever had in my entire life. I don't even know what it tastes like. I just know that somebody made me eat it when I was a kid, and now I hate the idea of it. Probably good. I don't know. Okay, next problem. It's actually the next problem. Let's try 1.6. Sorry, 1.6.16 D. So that's in the next problem. Um, Hold on. I mean, this is kind of too easy. Oh, yeah, yeah, yeah. Let's try this. Actually, I changed my mind. We're going to do B here on this one. Okay. So again, it's the same type of problem. So valid, like correct or incorrect. So what do we have? So this one is a convertible car is fun to drive. All right. Isaac's car is not a convertible. Why is Isaac so hard to spell, by the way? Isaac's car is not a convertible. Therefore, Isaac's car is not fun to drive. All right. So again, you need to write this in symbols, and then you need to try to write out the argument and see if you can tell if it's valid or invalid. So what are we going to do? We need some predicates and stuff. So let's say, so we're talking about, uh, what do we have? So a car can be fun to drive, and a car can be a convertible, right? So let's say like C of X, X is cars, X is a car, a car. X is a car. And then C of X will be X is a convertible. F of is X is fun to drive. So we don't really need we don't need a predicate for like we could have like I of X, and that could be um, like X is Isaac's car, but we don't really need to do that because this argument is really only talking about one specific car, Isaac's car. So um, we can write the argument like this, and we don't need an extra predicate. So so the original argument is, what is it? So a convertible car is fun to drive. So that would be for all X, for all cars, if it's convertible, then it is fun to drive. So convertible implies fun. Okay, that's the first line. The second line is Isaac's car is not a convertible. So you would just do not convertible. What's not a convertible? You just say like Isaac's car, like that. So I don't have to do anything special to like say that a car belongs to Isaac. We can just refer to the car and call it Isaac's car. What car? Isaac's car. Okay. So not C Isaac's car. So Isaac's car is not convertible. And then the conclusion supposedly is therefore Isaac's car is not fun to drive. Therefore, not fun. Isaac's car. Okay, so that's their argument. And then the question is it valid or is it correct? Right? And so how do we do it? Well, again, we just try to write it out and fill in the missing steps and see if we can. So we have line 1 for all x, c of x implies f of x. We have the second line is not c Isaac's car. And we're going to try to see if we can get to the conclusion. So we don't have the conclusion yet. So what would we do? Really the same thing we did in the previous problem, right? This top line here, for all cars, this is true. So this must be true for Isaac's car too, right? So if we put Isaac's car in for x, this would have to be true. So let's write this out with Isaac's car in and use that universal instantiation. So that top line is C of, I'm just going to write Isaac's car. Well, I was going to not write the whole thing, but I just did. So C Isaac's car implies F Isaac's car, right? And that is from line 1, and that's universal instantiation. That's where you fill in a specific example into a for all situation. Okay, now here's the thing. If you look at lines 2 and 3, we want to see if we can reach a conclusion. We were able to last time, right? Because we had like the two lines that are highlighted green here come together in a modus tollens. But we've got like modus ponens and modus tollens. And so like what modus ponens is this, right? P implies Q and P, therefore Q, right? So that's one, that's like modus ponens. And then modus tollens was P implies Q, not Q implies not P. Okay, so the thing is if you look at these, right, here you have the P and the P. If those match, you have Q. Okay, but these two do not match, right? Because this is not C and this is C. So these don't match the way these match. So it's not modus ponens. So it's not this. I don't like that color. Switching it. So it's not modus ponens because of these two. Now, for modus tollens, it's not, and it's these two, but they're opposites, right? Q and not Q. But here we have F, and this is not F, right? It's not C. So, oops. So that's not modus tollens either. Because modus tollens is these two kind of match. I mean, they match, but then they're opposites. Well, this does not match this at all. So it's not modus ponens and it's not modus tollens. It's neither one of those. And if you look at your other logical equivalences, I don't think you're going to find it. Okay? And so I don't see how we can make a conclusion here, right? I don't think we can. So you can't continue, right, past a certain point. You write this much and then you say at some point you're stumped and you just go, I don't think we can get to. What are we supposed to get to? Not F Isaac's car, right? All I did was I thought about the logical equivalents as we know, which are in the notes and they're in the book, and I just don't think we can get there from where we are. So you give up. And so once you give up, then I say, so argument is not correct, I'm going to guess. Okay, but hopefully you see what I was talking about before we did this problem, right? I'm giving up and I'm saying that the argument is not correct. But it's also possible that I just don't know how to get there. Like there could be steps to get you from line 3 to the line we're supposed to get to, and I don't know what they are. So I'm going to assume that I'm correct, and there is no way to do it. Okay? So that's how you do those. Let's see here. I think those are the only two that I specifically wanted to do from this section. So we'll go ahead and we'll look at some more proofs, which is section 1.7. And I'm going to pick just a couple of proofs that do things that we maybe haven't seen before or different problem types. So you don't have homework on this assigned yet, but that's fine. Okay, so let's try one. What do I want to try? Okay, yeah, I want to do one of these, an if and only if. So we're going to try 1.7.26. So the reason we're doing this is because it has an if and only if, and we didn't prove anything that was if and only if when we did proofs. So what are we proving? We're proving this. Prove if n is a positive integer, then that's not actually part of like, I mean, that's just positive integers. It's just kind of the universe. Then, where am I? N is even if and only if seven n plus 4 is even. All right. So before we start this proof, you need to know what the if and only if means. And so remember that P if and only if Q, which by the way gets abbreviated this way by most people, IFFQ. So that's kind of a shorthand. PIFFQ means P if and only if Q. What that means is it means that P implies Q and Q implies P. That's what if and only if means. So like the arrow goes both ways, right? Like P if and only if Q, like that. Okay. Which this is another, this and this are both shorthand for if and only if. And this is what it means. So whenever you have a proof that's if and only if, basically you have to do two proofs. Okay. Um, so we have to prove for positive integers, there's two things we have to prove. In even implies 7n plus 4 even, and we have to prove it the other way around. 7n plus 4 even implies n even. And so we have two actual proofs that we have to do to prove an if and only if statement. And, that doesn't mean it's harder or anything. It's just basically two proofs that we have to do. So now that we know it's two proofs, we have to prove both of those, then we'll go ahead and get started. So proof. All right, so what do we need? We need n to be a positive integer, okay? And we'll do this side first. Okay, so let n be a positive integer, and also we want n to be even. Okay, positive integer and even. Okay, now what are we supposed to do? Well, we just assumed this. Oops, that's not what I wanted. We just assumed this. And so, right, that's what we did here. And so then what we're going to do is we're going to prove that 7n plus 4 is even. So let's look at 7n plus 4. Then actually, before we look at 7n plus 4, the fact that n is even means what? N is even, so n must equal 2 times another integer. So I'll say n equals 2k, where k is even. No, that's wrong. Where k is an integer. All right. Now, normally we had an n right here, which might make this be looking a little confusing to you, but we're just kind of mixing around the letters. I just did it the way that it's written in the book. So we have what we have. Okay. So this is due to the fact that n is an even number, and this is just the definition of even. So I haven't really done anything yet. Now we want to look at this 7n plus 4. So 7n plus 4 is equal to, well, we know that n is 2k. So we can take this 2k and put it right in here for n. Right? So we have 14k plus 4. And remember what we did for even numbers in the previous lecture? Basically, you want to factor out a 2, and that's how you show that something is even, is if 2 goes into it evenly. So take out a 2, and you have 7k plus 2, which this is 2 times some other thing. So like what number are we going to call it? Like, I don't know. Like we can say 2p for integer p equals 7k plus 2, right? And then you're supposed to be able to look at this and say, well, obviously, if 7n plus 4 is actually equal to 2p, then 7n plus 4 must be even, right? Because it's 2 times an integer itself. So 7n plus 4 is even by the definition of even. All right. And so we did proofs just like this in the previous section. The only thing that's different right now is I'm only half done with my proof because I did just this half. Now I have to go back and I have to do this half. Okay. So our second part. So you don't have to say it's a second part, but our second part of the proof. So our second part is 7n plus 4 even implies n even. Now here's the thing. You don't want to prove this. We talked about this in the previous section, but it's really hard to go this direction from here to here. That's going to be hard to do. So you don't want to do that. You don't want to try to do that. Instead of proving this the way it's written, you actually want to prove the contrapositive. Whenever they put the complicated thing over here on the left-hand side, that probably means you want the contrapositive. So what I'll do is I'll say, we will prove the contrapositive instead, which is equivalent, so it doesn't matter which one we do. Now, remember how contrapositives work. Contrapositives are these. So like the contrapositive of P implies Q is not Q implies not P. So you reverse the order and you add a negation. So, if you take these and you swap the order and add a negation, it's the same thing really. These are logically equivalent. So I can, instead of proving this, I can prove not in even implies not 7n plus 4 even. And remember, not even for integers just means odd. So really, you're proving n odd implies 7n plus 4 odd. And that's not going to be that hard, actually. Actually, it's kind of interesting, right? This is what we're going to prove. And that's almost the same thing as we proved up here, right? Just we proved n even implies 7n plus 4 even. And now we're going to prove n odd implies 7n plus 4 odd. And somehow that is actually the same as what we have here. Weird. But this is what we're doing. So this is actually what we're going to prove. So let's try to prove that. So back to our proof here. So our proof, we're going to say let n be even, no, sorry, an integer, positive integer, be a positive, I guess, odd integer. Okay. And now we need to show that 7n plus 4 is odd. But before we do that, what's odd? So n is positive odd integer. So n is like 2k plus 1. And it's okay that I'm reusing the k here. Like I kind of finished my previous proof. I don't really need to use a different letter. If I want to, I can, but I think most people will understand that we're on to a different proof, even though this proof is part of our old proof. So n is a positive odd integer, n is 2k plus 1, and we need to prove something about 7n plus 4. So 7n plus 4 is equal to, let's fill in the n equals 2k plus 1, right? This is going to go in right there. 7, 2k plus 1 plus 4. Multiply that all out. 14k plus 7 plus 4. So you have 14k plus 11. Now what you have to do is somehow show that this is odd. And so to show that this is odd, you need to make it look like 2 times something plus 1, right? That's what odd looks like, something like this. So you need to separate out a 1. So if you need it to be odd, you need to separate out a 1. So even though I have 14k plus 11 right now, when I multiplied everything out, that's the same as 14k plus 10 plus 1. Okay, and then what we do is what we did on the other one, where the part that's left, you can factor a 2 out. So you have 2, 7k plus 5 plus 1. And then the thing in parentheses, the 7k plus 5, that's an integer. So that's 2p plus 1 for integer. That's p equals 7k plus 5. And now, if you have, let's get a different color here. 7n plus 4 is actually equal to 2p plus 1. That tells you that 7n plus 4 is odd. So 7n plus 4 is odd. Okay, great. So we did it. So we proved we proved this just now. We proved it the other way around. We proved the contrapositive of it, but that's the same. And we proved this in our first little half of the proof. So we actually proved both of these. So I can say, I'll write it out, since we proved n even implies 7n plus 4 even, that was the first proof. And the second proof established that 7n plus 4, even implies n even. That's not how we proved it, but that's the same thing. That was both ways. We know n even if and only if 7n plus 4 even, because we proved it with the arrow going both directions. And that's what we were trying to prove. This is if and only if. So that concludes our proof. Okay. And That's an if and only if proof. So, they take twice as long. They're not twice as hard, but you just every if and only if proof is basically two proofs. Uh, one for each direction of the conditional statement. Okay, so we did that. What else do I want to prove? Do I want to do that? Yeah, I guess I do. Where did they have the pigeonhole principle? Hold on. I want to see how they write it. It's a little bit weird. Correct proof. I don't see it. I don't see it. Okay. Um, I'm gonna write it down. I do not see it here, but like they expect you to do it in the book. So um, I'm just gonna write it, and you can just cite it. So pigeonhole principle. It's actually a very easy concept. So suppose you have to put five things. Actually, you know what? I'm going to use specific things. Five X's into four boxes. Okay. So where are they? One, two, three, four. Four boxes. And you have to put five X's into those four boxes. Okay. Now, how could you do it? Well, you could put all of them into one box, right? And then you have a box with five things in it. Or you could spread them out, right? You don't have to have that. You could have like two there, couple there, one there, right? You could have that. Okay. But there's a pretty basic concept that because we have five X's and we have four boxes, there is no way to do this where um, where one box does not have at least two things in it, right? So let me just write it in words. Because you have more boxes. No, that's not true. More X's. Sorry. Because you have more X's than boxes. One box must end up with two or more X's, right? You can't have one in each box, right? Because you go one, two, three, four. Now you need to put a fifth one somewhere. There's nowhere to put the fifth X without adding it to a box that already has an X, and one of the boxes ends up with two. Okay, so that's the pigeonhole principle, right? So pigeons and pigeonholes is what the original thing was. So that's just the idea. So yeah. So where would you use it? So for example, um, and this is true for anything. I'm not going to write out like a formal definition of the pigeonhole principle, but that's the idea. So like on example 1.7.22 says if you pick three socks from a drawer containing only blue socks and black socks only, blue socks and black socks only, you must get uh, two blue or two black socks, right? You have to get a pair that match. Um, and that's that's pretty simple, right? So you can just formulate it in terms of the pigeonhole principle. You can say, we are choosing uh, three socks, right? Those are our pigeons in this example, uh, from two colors, and so that's two pigeonholes. So those are the holes. So by the pigeonhole principle, we write that slightly easier to read, maybe if I can. So by the pigeonhole principle, one hole, which is colors, uh, must have two pigeons, at least two pigeons, which are socks. So that's complicated, but basically we have two socks of the same color. All right. And that is the pigeonhole principle. Um, they, I don't think they actually talked about the pigeonhole principle in this section. So I expect that they wanted you to do was they wanted you to um, consider all the cases. So they may have wanted you to do it this way. So they may have wanted you to list all the possibilities, right? So like if I use like if um, B equals blue and like BK equals black, right? Then they may have wanted you to do this, right? So choose three socks, and all of your possibilities are like you could go blue, 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 or blue, blue, black, or blue, black, blue, or blue, black, black. Okay. Or black, blue, blue, black, blue, black, 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 blue. Is there one more? Yeah. Black, black, black. Is that all of the different ways? I think I have all of them here, right? So you choose three socks. So like this is your first choice, second choice, and your third choice when you pick socks. Okay. And then you can just say in each case, right? Every case, in every case, you end up with a pair that matches, right? Of course you do, right? So there's two that match, there's two that match, there's two that match, there's two that match, two that match, two that match, two that match, two that match. So no matter what, you end up with two that match. And it's because of the pigeonhole principle. right? If there's only two different colors and you pick three socks, you have to come up with the same sock color twice, right? And it's just the pigeonhole principle. But you can do it without the pigeonhole principle just by thinking your way through it. But the pigeonhole principle makes things easier, so that is why I did it. Okay, let me look for one more thing here. Um, yeah. Are there any that I want to do? I think actually, I mean, maybe that's enough. Oh, no, 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 no. Sorry, let me just take 1 second here to look. Yeah, okay. So like, let's see, you can extend the concept too. So I'll just note. So you can extend the pigeonhole principle to, how would you do that? Well, like, for example, um, let's say if you choose 15 days, right? Um, then is that what I want? No, I don't think that's quite what I want. Um, let me just do one that's actually in the book. Yeah, so let's just do this. Um, choose 25 days on the calendar. They must, or three, sorry, three must fall in the same month. Why? Well, just think about it, right? If you make your calendar, which has 12 months, so um, January, February, March, April, May, June, July, August, September, October, November, December. And yes, I know that I just like repeated letters and stuff, but from context, we'll be able to figure it out. And so, simple idea, you need to put 25 days in here. So every time you pick a day, it falls in a particular month, right? So like you put a day in January. Okay, where's the next one go? Well, you could put it in January again, right? But let's say you're trying to spread them out as much as possible. So you don't do that. You want to spread them out as much as possible. So you go, okay, we picked one. Here's another 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 one, right? You don't have to fill them out in order, but if you're trying to spread them out, after you do 12, you've got 12 of them all spread out, one per month. Did I actually do that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That looks really weird. Okay, so I picked 12 days and I picked one day per month, right? But I have to keep picking days. So the pigeonhole principle tells me that when I pick the 13th day, the 13th day has to go in a month that already has a day, right? So, like, if you picked 13, you would know that one month has 2 days, right? So, like, I picked at this point 13 days, and the way I drew it, October has 2 days, right? But let's say I keep picking days. I'm trying to get to 25. So I keep picking days and I want to spread them out as much as possible. So I have 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So at this point, I've picked 24 days, right? And I spread them out as much as possible. But now I have to pick a 25th day. So I pick a 25th day. Where is that day going to go? Well, I can put it in any month I want, but no matter what month I pick, like let's say it's March, one month has to end up with 3 days, right? One month has to end up with 3 days. You spread them out as much as possible, but that's just how it happens. Okay. And so that's still the pigeonhole principle. So you can just say, you know, you spread out the days as much as possible, or even if you spread out the days, it's still impossible not to have a month with 3 days. Right? And that's still the pigeonhole principle. It's just instead of having, um, one extra day, you have you fill up the whole thing twice, and then you still have extra, and that's what makes it go to three. So yeah, I mean you can try to explain that, but that's the pigeonhole principle, extended. So yeah, all right. So I think that's everything I wanted to say. We're over an hour, so we will stop this lecture here. Good luck with your homework. Come to office hours if you need help.